Based on the sequences below, write the recursive routine and find the 10th, 20th, and n terms for each sequence. Starting on the left, we can see that from term to term, 3, 7, 11, 15, we are adding for each time, but that first term is not what we would start with the recursive routine. We have to backtrack 1, so we really want -1, enter answer +4, enter, enter, enter for that routine, which could help us get the nth term. Once we have that, we can translate that to -1 + 4n. Then once I have my pattern, I can just substitute in the value for n, the term that I'm looking for, into that pattern. So I can put a 10 in for n, a 20 in for n, and see what results. If I put in the 10, I get a 39, and if I put in the 20, I'll get a 79. Now, similar to the other side, I'm looking at 256, 192, 144, 108. Here, I'm not adding or subtracting a certain value, so I want to see what kind of ratio, perhaps a multiplier, is involved. In order to do that, I would take the current term divided by the previous to see what I would be multiplying going forward. So what's 192 divided by 256? 144 divided by 192, 108 divided by 144, and that will help me find my pattern. Again, this is my first term. I would have to backtrack one more to find my 0, and I can establish my recursive routine and my expression for n from that. So in doing so, we can see the multiplier is 3/4. Our original value then, if I take 256 divided by 3/4, it's 1024 divided by 3, which would translate into, for any term, n, taking 1024 thirds times 3/4 to the power of n. So if I put 10 in for n, that would be approximately 1.9222, or its exact value would be 19,683 divided by 1024. When I put 20 in for n, I get approximately 1.0824. There is no exact value for this one. Now, if you notice, we had two different types of patterns going on. One we were adding and one we were multiplying, and that refers to the types of sequences that we're using. If we have something that we're adding or subtracting, that would be called an arithmetic sequence because there is a common difference. Now, if it had a multiplier, we could call that a common ratio. That would be considered a geometric sequence. So as I look at my two sequences, the one on the left would be considered arithmetic because it had that common difference of 4 every time. And the one on the right would be geometric because it had that common multiplier, that ratio of 3/4. So as we go forward, we're going to start pulling in, asking, not only can you find the recursive routine, the expression or equation to represent the pattern, finding different terms, but what type of sequence does it represent, arithmetic or geometric? So we're getting into a couple of examples now, saying that Macy's is selling a suit for $500. Each week, the price of the suit will be reduced by 15%. So what we're going to do here is a couple of things. We want to make a table of values and graph. I would suggest doing at least 7 weeks of data to help you think about that. Then we'll come up with the recursive routine, writing an equation if we can, and then doing some predictions like when will the suit cost $75. So if I'm thinking about how this is going on, making my table of values, my explanatory variable would be each week that passes. The response variable would be the price of the suit. So I'm just going to collect the data, saying, okay, if I'm starting with $500, I'm losing 15% every week, what would that look like? And then I can plot those 7 weeks. So what I did to expedite the matter is I went to my applet, I put in the first 7 weeks here, actually, yeah, for 7 weeks when after the sale started, and the price of the suits. And so here's my data here. And so this would be the original price of the suit, right? And the 7 weeks after that it's been on sale. And as you can see, we have our individual data points. They are not connected because we have individual prices every week. We're not looking at a daily change, so we're going to leave them separate. So it's not a continuous graph, but it is a discrete one. And so I'm going to use this to come up with the recursive routine. So I know for this one, the starting price. So I have the zero term of 500, and every week I was losing 15%. So how can I show that? Well, what you guys probably did was took 500, enter, times 1 minus 0.15. We always start with percentages, the 100%. We either add to them or take away. If I'm reducing it by 15%, I'm losing 15%. And percentages are always out of 100. So 100 out of 100 is the 1, the original. 15 out of 100 is our 0.15. And I know we've talked about this before. Now, the other way to think about that is if you started with 100% and you lost 15%, well, that means you're only keeping 85% of the price. So I could take 500 and multiply that by 0.85 every single time over and over again and accomplish the same goal. Now, I have the original price of the suit, my term 0. I have my common multiplier. So could I write the equation? Of course we can. We have all the pieces. We have the output for y, right, the price, coming from 500 times the multiplier, whichever format we're using, over and over again, so it has to be an exponential. So this would be if you did the 1 minus 0.15, or if you're showing that you only retained 85% of the cost. So it's saying, when will this suit cost $75? Money, the price, is your response variable. That is what we were using for y. So I'm going to replace y with 75 and find a way to calculate for x, the exponent. So we've talked about this in the past because it's an exponential equation. To undo that, you would have to use some logarithms. And depending on your skills with logarithms, you may be more comfortable using another method to help you solve. And we did this with our bungee jump. Whenever we had an output and we're trying to find an input for the function, we could do this graphically. So what I would do is I would put my function, the 500 times the multiplier to the power of x in y1, and then I would put 75 into y2. Then I would set my window. So if you were doing this on Desmos, you could click on the wrench and adjust it. And again, if we think about the explanatory and response variables, explanatory is the number of weeks. And so technically we can't have negative number of weeks. So maybe we would want to set our window from like -1 to, at that guess, for our maximum, just so we can see what's happening at 0. And then our explanatory variable, that was our number of weeks, we can, when we talk about guessing that, then our response is the price, right? So the lowest price we know would be 0, right? And they're not going to give it away for free. So that could be your y minimum. Your y maximum, we would definitely want it above 75. You might even want to set it a little bit above the original price of the suit, just so you can get the whole experience of the function. Now, this is going to look a little bit different on Desmos than what you did maybe in the applet, because it's tracking time as if it was continuous. And we know that it's being tracked by weeks, so we're going to have to give a little bit of leeway with this. But again, because we're looking for the system of equations where they're equivalent in the same place, same time, we're interested in seeing that intersection point. So I can see it here. So on Desmos, I can just use my cursor and click on it. If you had your graphing calculator, remember you have the steps given to you with your systems of equations. You still have your y1, y2, but you're pressing second, trace, intersect. It's going to ask you for first curve, second curve, and guess. After each one, just press enter 3 times, or enter each time. So that's 3 enters, and it will give you the same result as what we see here. Now, the question was, when will the price be $75? Well, here I see 11.673, and because we're measuring in weeks, I can't have 11.6 weeks, so I'm going to have to go to my 12 weeks to really answer that question. So we know after 12 weeks, the suit will be on sale for the $75. Now, what's nice about the Desmos is we can see the exponential pattern coming into more fruition here because we have more weeks than it's happening than the first 7. But if we compared it back to our original scatter plot, we could have started to see the curve developing here with our individual data points. So again, that's telling you that you have a geometric sequence over the arithmetic, which would be more linear. Now we had one more question saying, how much will the suit be after 20 weeks? So if we think about our equations, our weeks, that was our explanatory variable, right, in terms of x. So if I know the number of weeks, I should be able to calculate the price just by doing a quick substitution. So if I put 20 in for x and do my calculations, I should end up with $19.38. All right, here's our second example. Someone left a sandwich in the classroom after final exams. That night, 3 ants came to eat the sandwich. Each night after that, 3 new friends joined them. So we're going to run through the same types of things. Can we make a table of values and a graph? Again, I'm going to suggest doing at least 7 nights to get an idea of how it's happening. Excuse me. Can you write the recursive routine, an equation, and then do some predictions based on that data? So based on the table, what I had for my explanatory variable, that was the days passed, and I just went from 0 through 7, and the number of ants that would be appearing. And so we know on the original day of the final exams, we had the sandwich left, there were 3 ants, and then each night after that, 3 more ants were going to come, and so these were my outputs based on my inputs. And here's my scatter plot. And again, as you know, with my scatter plot, couple pet peeves, we really should have a break in our y-axis here. I use the applet for convenience, but we really should be able to count from like 0 above by 2s to make that happen. And technically, we should really have the y-axis here. But anyways, here we can have an idea of the first 7 nights or days that has passed when we're talking about the sandwich being left behind. So in terms of the recursive routine, remember when we left the sandwich that day, there were 3 and then 3 more after that. So we would have 3 and then our answer plus 3 over and over and over again. And I'm going to write the equation to represent that. That would be y equals 3x plus 3, or maybe you want to write 3 plus 3x. If you're sticking with our linear models that we had before, where the y-intercept was listed first versus second. And remember, for us, our explanatory is the x, and our response was the y. Now we want to say how many ants are in the room 2 weeks later. And here we have to be careful because we're talking about every night, and now we're in weeks. We have to pause and say, okay, well, how many nights are in 2 weeks? So that would be 14. And what type of variable is it? If we're talking about the nights, we said nights were going to be the explanatory variable. So that means they're telling you the hint that you have the x value. So if I put that in for x, we're going to see how many ants we had. So with a quick substitution, we find out that there will be 45 ants in the room after 2 weeks. The next thing we want to look at was when the ant population will reach 100. So again, what is this telling us? This is the response variable. Y is 100. Could we solve for the number of nights where that would happen? And we can, because with a quick substitution, this is a arithmetic sequence, so we have a linear type equation. We can undo this to solve for x. We would subtract 3 from each side then we have to divide by 3, and then see what happens. So we could tell on the left-hand side that's not going to be an integer. So if you're using your calculator, you probably saw something like 32.3 repeating. Otherwise, that's 32 and 1/3. And we have to stop and say, okay, well, what did that x, that explanatory variable, represent again? That was the number of nights, or the number of days that had passed. And we can't really have the 0.3, so we're going to go up to the next increment. So we're going to say after about 33 nights, there should be 100 ants in the room. All right, so you've been working with your arithmetic and your geometric sequences the last couple of days. And so for your practice now is you're going to look at the next situation, doing a construction. So we have the idea of like a tree and branches. So here is the trunk of the tree, and here are the branches that come out. So what we're giving you here is your first stage. This is stage 1. So if they said how many branches, I would say 2. Now it says you're going to draw excuse me, 4 new branches for stage 2 by connecting the endpoints to the appropriate dots on the grid. And we know that the branches are going to be half as long as the current length. So you're going to count how long it is, and then going 60 degrees. So that's why you have your isometric dot paper. It's in your degree increment. You're going to build off your branches and then record your data in the table. Once you get your data, the goal is to come up with an expression to represent it, or a formula, list out the terms 6, 7, 8, and 9, and then be able to give me a graph for those first 5 terms in the sequence. If you decide to continue using the applet to make your scatter plots, just make sure you're snipping it on your Chromebook and inserting it into ClassKit. If you're doing it on paper, do your sketch to make sure everything's labeled. We have the explanatory and response variables labeled. We also have, and when I say labeled, as in the context of the problem, you also have a consistent scale to represent your graph.